Okay, so we're going to start with our introduction to conic sections. Okay, basically the different types of graphs that can come from a cone, right? The word conic is a derivative of the word cone. So in each of these cases, these come from some type of a cone. Okay, so we want to identify them from your equations. Okay, looking at the clues given to you in your equation and also sketching them from its own standard form. Okay, every conic has its own standard form. And it's important to be able to recognize which conic is which based upon the equation. So here are some things that we should talk about. Okay, 4 of them that we're going to study. There's a couple other ones, but those aren't really that important. So notice here, if you take a line, right, a slanted line, and this would be like your origin, and here's your slanted line, and you rotate that line around the x-axis, you get this double-sided cone with a top cone and a bottom cone. Okay, normally we only talk about one cone, but there are actually 2 of them here. So, and depending on how you slice this cone, right, what's the cross section of your cone, you're going to get 4 different types of pictures. So looking at this one, if you cross the cone parallel to its base, okay, so this would be the base, this round object here, and every cone has a cross section that's a circle if you cut it parallel to its base. Okay, you get a circle. Okay, now granted this is in perspective, so of course it doesn't look like a circle, but it would be a circle if you were to be looking at it from the top view. It would be perfectly round, and the distance from the center everywhere else would be the same. So parallel to its base, you get a circle. Okay, if you slice it somehow not parallel to its base, all right, and this is to the base, you're going to get an ellipse. Okay, this one here is your ellipse with 2 L's. Okay, it's important to spell math words right. So if you cut it not parallel to its base, okay, at any type of an angle from, between parallel and another parallel, you're going to get an ellipse, which has one side longer than the other for an ellipse. Okay, if you cut it parallel to its side, so this is the side of your cone. If you cut it parallel to its side, you're going to get a parabola. Okay, so a parabola is a shape that you get when you cut it parallel to its side. Okay, we've done parabolas since Algebra 1, but maybe we'll add a little bit to it here. And then the last one, if you cut it perpendicular to its base, okay, you get a double-sided graph. Okay, notice these are 2 sides, and this will always happen whenever you're cutting it perpendicular to its base, because there's a top cone and a bottom cone. Okay, and this is the one that really shows that. You get something called a hyperbola when you slice it parallel to, or rather perpendicular to its base. So here you see the general equation. Okay, so this is the general equation for all of our conic sections. Okay, and actually it's the general equation for every single, just conic sections. I'm not going to say polynomial, because polynomials only have 1 variable, where these have 2 variables. Okay, so there's the x squared, and then the y squared, and then the x thing, and then the y thing, and then a number and equals 0. So your equations are going to start off like this. Almost all of them are. Okay, so depending on the coefficients and the powers, you have different types of equations. So for a circle, we start off with a circle. The uniqueness about a circle that you're going to look for, okay, is identifying is that the coefficients of x squared and y squared are equal. Okay, nothing else really matters as long as the coefficients of x squared and y squared are equal and they are being added together. Okay, so this is what we're looking for. This is what we're trying to identify in our equation in order to have a circle. These coefficients, a and b, must be the same and they have to be added together. Okay, but then standard form is going to look like this. So this is our standard form for a circle. Okay, it has parentheses around your x terms with a squared value. You have parentheses around your y terms with a squared value, equals the radius squared. So this one always equals a number on the right side for a circle. Okay, most of the time it's a perfect square like 25 or 16 or 49 or 144, but it does not always have to be. This does not have to be a perfect square. Okay, so from this equation we can get the center. So the center is h comma k, always opposite from your parentheses. So if you had a -5 in here, you would have a +5 as the coordinate. If you had a +9 in here, it would be a -9 as your coordinate. So anytime we have parentheses and you're trying to find the centers, they're always the opposite values because parentheses lie, as we've learned for a long time. So we can find the center of your circle and we can find the radius, which is the square root of whatever number this happens to be. Okay, that's the radius. So this is our circle. We're looking to see if the coefficients are the same and if they're being added together. Okay, to identify the equation as being a circle. Now, how about a parabola? Okay, a parabola only has one squared variable. It can be x or it can be y, variable. I could spell this morning, variable. It can be x squared or it can be y squared, but it only is going to be one. Okay, it can be positive, it can be negative, but there will only be one squared variable. Okay, that's how you know it's going to be an ellipse. Either x squared or y squared. Neither both of them. Okay, and there's a very strange standard form. So if the x is squared, x minus h squared, then the y value has a factored thing in front of it. Okay, just like this. X minus h squared equals 4p. Okay, and we'll talk about what p is in a little bit, but 4p out here times y minus k, just y minus k, no square. Notice only one variable is squared. Okay, or if it's the y thing that's being squared, then the 4p goes in front of the x parentheses, if there are any. So we can be x squared or y squared, and we're still going to have a parabola. Okay? And the factor always comes with a non-squared parenthesis. But notice the center is still hk, or the vertex in this case. All parabolas have vertices or vertex. The x coordinate still comes from the x parenthesis, and the y coordinate still comes from the y parenthesis, regardless of which one is being squared. Okay, so if it's x is being squared, then these are opening vertically, just like they've always done, y equals x squared. But if y is being squared, it's opening horizontally. Okay, positives go to the right and negatives go to the left. Okay, so that's how we can tell if it is a parabola. You have one squared variable. And we'll talk more about how we write it in standard form later. Now for an ellipse, the coefficients are not equal to each other. No matter what they are, the coefficients will not be the same. Okay, and we also are adding the two squared things together. So that's how we can tell if it's an ellipse. Okay, your coefficients are different, but you're still adding them together. And the rest of this stuff doesn't matter. The x and the y and the e, this constant number here, these can be whatever you want them to be. They will matter when we start finding the centers and radii and stuff, but for the equation, they don't matter. We're only looking at the squared terms and the squared terms coefficients. Now, for an ellipse, these ones look very strange, maybe. Okay, so we still have the center, x minus h and y minus k, and they're still being squared. But notice in both of these cases, they have denominators, and they equal 1. So this is one of the main differences that separates it from a circle, is a circle will always equal a number. Well, it can equal 1, but it will equal a number over here and have no fractions, no denominators. Where an ellipse, you want to have denominators and you want it to be equal to 1. So there's a couple extra steps when we're doing it from a circle to make it into an ellipse when we're going to do it. Well, that'll be tomorrow. Okay, but this is the standard form for an ellipse, where your center is still at h comma k. The h comes from your x parenthesis and the y comes from your y parenthesis. And then the numbers on bottom will be your, basically the lengths, your major and your minor axes, right? Because you're no longer going to be circular. It's going to have one side longer than the other, which will make it into an ellipse. And then the last one here, our hyperbola. You can notice in a hyperbola, because it's x squared minus y squared. There's a minus in here. Or it could be y squared minus x squared. As long as one of them is being subtracted, you have yourself a hyperbola. Okay, and this will determine whether it opens left or right or up and down. If x squared is positive, it opens left and right. And if y squared is positive, it opens up and down. But we'll talk about that more later. So the coefficients don't matter. In a hyperbola, all you're looking for is a subtraction sign in between your squared terms. Okay, we're looking for subtraction. So for a hyperbola, it looks exactly like an ellipse, except for it has a minus in between these terms. And that's how we can tell that it is a hyperbola, because it is being subtracted. And it equals 1, just like an ellipse does. So circle, parabola, ellipse, and hyperbola, they all have a standard form and some clues that we're going to look for. That'll be easy. So here we have 9 general equations. Okay, so number 1, looking at the coefficients. Okay, this one's a 3 and that one's a 4. That means they're different. So this should be what type of a conic equation?
Ellipse.
An ellipse, yes, this is going to be an ellipse because these x squared and y squared are different. Fantastic. Okay, what about number 2?
They're being subtracted, so it's a hyperbola, the x and the y.
Yes, great. So we notice there's a subtraction problem here. So this is automatically going to be a hyperbola, regardless of the squared coefficients. Because there's a minus, this one's a hyperbola. Okay, how about number 3? What do you notice about these terms?
So circle?
Yes, this is indeed a circle. Okay, anytime the squared variables are the same, you have yourself a circle. Okay, how about number 4?
Parabola?
Yes, this will be a parabola. We notice there's only one squared term. So this is definitely going to be a parabola. Only y is squared. Okay, number 5. What do we notice?
Hyperbola.
Subtraction.
Right, we notice a subtraction, so this is definitely going to be a hyperbola. Regardless of these being the same coefficient, there's a minus, so it's going to be a hyperbola. Okay, number 6.
There's only one squared variable, so it's a parabola.
Fantastic. One squared variable means it's a parabola. Okay, how about number 7? This is a short little equation.
It's an ellipse.
Yep, this is an ellipse. Your coefficients are different and it's added together. Okay, number 8.
It's a circle.
It is a circle. The coefficients are the same and it's added together. And lastly, number 9.
Subtracted, so it's a hyperbola.
Subtraction, so it's a hyperbola. So those are the clues you're looking for. You're looking at pluses and minuses, you're looking at coefficients, and you're looking at how many squared things there are. That's how we identify these conic sections from a general equation. So our first equation is parentheses x minus 2 squared plus parentheses y minus 5 squared equals 16. So hopefully you are able to recognize this as being a circle, because this is the standard form for a circle. So there are 2 things we need for our circle. The first is our center. Okay, so the center comes from your x parentheses. This is a minus 2 in parentheses, so it's a positive 2 when it comes out. And this is a negative 5 in parentheses, so it's a positive 5 when it comes out. So we have a center at 2, 5. So 2 units right and 5 units up. Okay, so we put a dot there and that identifies it as its center. And then we have to find the radius, because every circle has a center and a radius. So we take the square root of 16 and that gives us a radius of 4. Okay, now here is the hard part. Well, no, not yet. That means we got to go 4 units in every direction. So we'll go 4 units vertically, 4 units up, and put a dot. We'll go 4 units to the right, being as evenly spaced as possible, 4 units left, and 4 units down. Okay, so we're basically putting some guideposts so that we can try and make this as circular as possible. Okay, so yes, I don't see many circles. I see lots of amoebas and some, I don't know, random shapes, but make it as circular as possible. There, that's a circle. Okay, this next one, if you'll notice, we have x plus 3 in parentheses squared over 9 plus y minus 4 squared over 25 equals 1. So hopefully you're able to recognize this as being an ellipse. Okay, so for an ellipse, we still have to find the center of our ellipse. And just like your circle, that's the opposite of your parentheses. So we have a plus 3 becomes a negative 3 coordinate, and a minus 4 becomes a plus 4 coordinate. So we have a center at negative 3, positive 4. So we put that on your grid. There is the center. Okay, now we have to figure out how far left and right we go and how far up and down we go. Okay, so the number underneath the x is 9, which means this is how far we go to the left and to the right. Is the square root of 9. Remember, the bottom number is a squared number. So to figure out how far we go, we take the square root. So we're going to go 3 units to the left and 3 units to the right. Okay, we're going to put dots there so that we can tell this is going to be the edge of your ellipse. So 3 units left and 3 units right. That's the number underneath the x term. So you go that far in the x direction. the square root of 9 left, and the square root of 9 right. And now we turn to the y direction, and we see there's a 25 underneath the y term. So this is up and down. We're going to go the square root of 25, or 5 units. 5 units up from your center, and 5 units down from your center. Okay? So the numbers in your denominator, when you square root them, that tells you the distance you should go from your center in the direction of the letter under which they are. Okay, so we have a 25 underneath the y, so we go 5 units in the y direction, up and down from your center, and you have a 9 underneath the x, so you go 3 units left or right from your center. Okay, now once again, do your best to make this as round as possible. At least your corners as round as possible. It should not look circular, but it should also not look so much like a football. Something like that. Okay, so this ellipse is taller than it is wide because the y values are longer, or rather bigger, than your x values. Okay, now there's a couple things to note here. Something called the major axis. So the major axis is your longer axis. So the major axis goes from here to here, which is now going to be 10 units. So your major axis is the longer of the two axes. So your major axis length is 10, and then we're going to have something called the minor axis, which is the shorter distance, which looks like in this case it's going to be 6. So your major axis is 10 units long, and your minor axis is 6 units long. And there's one more thing that we need to do, and that's called something called the foci. Okay, so the foci are 2 dots or 2 points inside of your ellipse that give it the it gives it a really special property. Okay, and we'll probably talk about that property tomorrow just to save some time. But to find the foci, we're going to do a subtraction Pythagorean theorem. Okay, c squared is the absolute value of a squared minus b squared. Okay, so we're looking at your denominators down here. Okay, your denominators are your a squared and your b squared. Okay, so in this case, we have 9 minus 25, which in absolute value is 16. So this number will always be a positive number. Okay, so c is 4. So what this tells you is that the distance from your center to your foci is 4 units. Okay, and this is always along your major axis. The foci always go along your major axis. So 4 units from the center puts a focus point right here, and 4 units from your center puts a focus point right there. Okay, for a circle, the focus is the center of the circle. It's the same spot, okay, which makes it nice and round and even and beautiful. Okay, the closer these foci are to your center, the rounder your ellipse is going to be. And the farther away they are from the center, the more stretched your ellipse is going to be. Okay, so these are the points that determine the ovalness, if you will, the ellipticalness of your ellipse. The closer they are to the center, the rounder your graph will be. And the farther apart they are, the more elliptical it will be. Okay, so we have to find the center. We find the lengths of the major and minor axes, and you plot the foci, which is plural for focus. And that's how we do our ellipse. So this one is going to be our hyperbola. Notice there's a minus. And the hyperbola we do very similar to your ellipse. We still find the center, which is at, notice there's no parentheses here, so that's going to be a 0 in your x coordinate, and a -4 in your y coordinate. So if there's no parentheses, then it's going to be a 0. So we come down 4 units. Okay, and that's going to be your quote unquote center, even though that part's not a part of your graph. But very similar to doing an ellipse, we have to figure out how far we go to the left and right. So that's going to be the square root of 36, which is 6 units. So you go 6 units to the right and 6 units left. Okay, just like with our ellipse, we put up these axes. And then to go vertically, we take the up and down, that's UD. You go the square root of 4, which is 2. So 2 units up and 2 units down in the y direction. So rather than making an ellipse, we make a box out of these values. Okay, we use these axes to make a box for hyperbola. Okay, so it looks like we would be making an ellipse, right, if we made it round on the inside here, but we are making a box. Okay, and what this box does is it allows us to sketch your asymptotes. So the asymptotes in this case represent the sides of your cone. Okay, and our graph is going to go and approach the sides of our cone. So your asymptotes go from corner through the center and out the other corner. So these are your asymptotes. We use our major and minor axes to make a box, and we use that box to sketch these asymptotes. Okay, so these go through your center from corner to corner. Okay, and out the far ends here. Now, because x squared is positive, right, our x squared is being positive here, this graph is going to open along the x-axis. Okay, so this one's going to open sideways. So this point here is now one of your vertices, and this point is your other vertex. So the graph will swoop in next to your asymptote, hit your vertex, and then swoop out back towards your other asymptote. Okay, on both sides, it swoops down your asymptote, hits your vertex, nice and smoothly, and then goes out towards the other one. Okay, make it look as curved as you possibly can. Okay, but these things, just like ellipses, also have foci. But this one is a Pythagorean theorem foci. We are adding them together, a squared plus b squared. Okay, so in this case, 36 plus 4 is 40. So the square root of 40 is about 6.4, I would say. Okay, so we get this focal length, and that means we got to count from your center 6 units, 1, 2, 3, 4, 5, 6.4 out towards your graph. Okay, so these are your two foci. They are the last parts of your graph, just like it was for an ellipse. So for a hyperbola, it's a squared plus b squared, and your foci are in the curve, right? They're inside of the curve of your graph, outside of the vertices, okay, farther away from your center. And for an ellipse, it's a squared minus b squared, which makes your foci inside of your ellipse. So when we're graphing our parabola, right, and this one's a parabola, it only has one squared thing, so it's definitely a parabola. We have to first identify the vertex. So the x-coordinate comes from the x parentheses, so positive 3, and the y-coordinate comes from the y parentheses, so negative 2. So our vertex is going to be here at positive 3, negative 2. Okay, this number 8 is positive and y is squared, so this graph is going to open to the right. Okay, it's going to open to the right because it's y squared and because we have a positive factor outside of your non-squared parenthesis, in this case the x. So this means it's opening right. So what we have to do is calculate the focus. So what we do is we take whatever number is outside of your parenthesis here and you set it equal to 4p. So p equals 2. So what that tells us is your focus is 2 units away from your vertex. And because it's a positive 2, that means it's 2 units away to the right, along the positive direction. So your focus is 2 units away to the right of your vertex, and then we have something called your directrix, okay, which is a vertical line. It is also 2 units away on the other side of your focus. So this is your directrix line. In this case, the directrix is x equals 1. Now, the last thing we have to do is plot something called the latus rectum, okay, which is a line perpendicular and fairly longish. Anyway, this length is your latus rectum. Whatever number is this is going to be the length of your latus rectum. Okay, now watch this. So if it's 8, we divide that by 2, and it's 4 units up from your focus. Okay, and it's also 4 units down from your focus. So the latus rectum goes through your focus. 1, 2, 3, 4, and this tells you how wide your graph is going to be. Okay, so here we have a lattice rectum length of 8 units, 1, 2, 3, 4, 5, 6, 7, 8. You have a focal length of 2 units and a directrix length of 2 units also. So then your parabola goes through your vertex and also through these lattice rectum points. Okay, so that's how we graph this parabola if it is in standard conic form. Okay, which is different than vertex form and different than anything else. Okay, so we have your focus, we have your vertex, we have your directrix, and we have your lattice rectum length.